This conference will now be recorded.
Very good evening, students. So yesterday in the last class we had discussed about the various type of magnetic materials like paramagnetic materials, and before that we had discussed diamagnetic materials and its origin. In the last class we had discussed the origin of paramagnetic material, Curie's law, like Curie law of paramagnetism, and we had discussed origin of ferromagnetism, etc. So today basically we'll be discussing about magnetic hysteresis, BH loop, and the usefulness of BH loop study of any magnetic material. What is soft and hard magnetic material, their uses, and we'll try to discuss few numerical problems or some questions from JEE Mains paper. So I just would like to recap one thing in relation to origin of paramagnetism. So there we had discussed few things like, see, this is the theory given by Weiss. So Weiss hypothesized that magnetic materials, basically the ferromagnetic materials, they have certain domains or regions. So we say magnetic domains, okay? And this is called sometimes domain theory also. So magnetic domain, okay? So ferromagnetic materials have magnetic domains. Here the spins are actually cooperative spins or dipoles are interacting. Okay, this may be the first point. Okay, spin or dipole are interacting. Then we said that a group of dipoles, they interact with each other and they cooperatively they orient in a particular direction in certain region. Okay, like this region, this region, this region. There are various regions, but point is that these regions are called domains anyway. So these are called magnetic domains. Magnetic domains. However, due to thermal energy or thermal agitation, these domains are randomly oriented. Okay, and because of that the net magnetization will be 0, and as you apply the magnetic field externally, then the domain walls, they rotate. First they rotate, okay, and then as you increase the field gradually, this domain walls will be actually, the favorable domains will be increasing. That means the domain which has direction, like which has net magnetization in the direction of applied field will grow up. Like this one will grow, this one will grow to the whole bulk of the material. Okay, and then you will get a single domain ultimately, and at that stage, this is the figure. So at this stage all the magnetic dipoles will be oriented in the field direction, and then you get the maximum magnetization, that is called saturation magnetization, saturation, MSAT, okay, or AMS, saturation magnetization. And Thereafter, if you increase the field further, you won't get any magnetization. Okay, this is what we had discussed yesterday. So one thing we had not discussed related to this paramagnetic materials, that is Curie-Weiss law or modified Curie law for paramagnet. You know, we have seen when we increase the temperature, experimentally it is seen that when the temperature of a ferromagnetic substance, as the temperature of a ferromagnetic substance increases, the net magnetization decreases. Okay, net magnetization decreases. Why? Because the domain walls become again random. As domain orientation of the domain walls, sorry, domain orientation of magnetic domains become random. Okay, becomes random due to thermal agitation. Okay, so as you increase the temperature, the net magnetization starts decreasing for paramagnetic material, and you know that happens due to the randomness of the domain walls, sorry, domains, magnetic domains. Now this randomness will increase as you increase the temperature again and again, and at some time the domain, see, domain will be totally random and it will act as paramagnet. Okay, just like your paramagnetic material. Paramagnetic material has permanent dipole moment due to atomic moment of unpaired spin. You will get, see, you have atomic dipoles, but because of randomness or random orientation of these vectors, dipole moment vectors, the net magnetization becomes zero. So in this case also, so ferro actually gets transferred to para. Okay, paramagnet. So this is temperature or heating. If you heat it, then ferro at higher temperature will become paramagnet. Okay, so this is what is expressed in terms of susceptibility. Suppose susceptibility, if we draw the curve susceptibility versus 1 by t, see susceptibility 1 over t, then you know how you get a curve like this. Sorry, you'll get a curve like, see, this will come and then this will be, there is a turn. Okay, so this is actually, and then it becomes maybe zero. So this temperature is called Tc. Okay, Tc. So there is a critical temperature, after which, because see, the paramagnet, in case of paramagnet, it should go like this, right? It should go like this through origin. For a paramagnet, this chi versus 1 by t should go through the origin. Okay, that should go through the origin. Okay, it is for para. Okay, para. but this is for ferromagnetism. Ferro. See, this is the temperature Tc. Okay, so it is becoming almost zero while before this zero temperature. Okay, I mean to say this becomes actually a paramagnet. Okay, before it is actually ferromagnet, and then so there is a non-linearity here. Non-linearity here. Okay, so mathematically, or this phenomenon was actually expressed in terms of chi is equal to c by t minus tc. So t minus tc. This c by t is just Curie law. C by t, just Curie law. This is Curie law of paramagnetism. But c by t minus tc. See, this is same Curie constant, but this is called critical. This is not Curie temperature. I mean, yeah. So you can say this is Curie temperature or critical temperature. This is Curie temperature. Curie temperature. This is called Curie temperature or critical temperature or critical temperature. Critical temperature. So below which it is actually ferromagnet, and beyond which it is paramagnet. Okay, beyond which it is paramagnet. All right. So what I wanted to say, that there is a Curie-Weiss. This law is called Curie-Weiss law as well. I'll just remove this and I'll write the. So Curie's law, Curie-Weiss law, or modified Curie's law, modified Curie law or Curie-Weiss law is actually applicable for ferromagnetic material, right? So, but simply Curie law is for paramagnetic material. So this I'll write here, C by T minus Tc. So this is actually modified. Let me erase this part. Modified Curie law or Curie-Weiss law. Modified Curie law or Curie-Weiss law. Okay. Now we'll go to next topic, and this is today's topic. We'll discuss uh, magnetic hysteresis and hysteresis loop. So, what is magnetic hysteresis? So, this is actually related to the relation between the magnetizing field or magnetic field intensity and the magnetic field intensity and the magnetic induction that is produced inside the material. Okay, inside a magnetic material. All right. So what happens? The relation between magnetic induction and magnetizing field or magnetic field intensity, that is H, is not linear. Not linear. So this is linear for paramagnet. Okay, for paramagnet this relationship is linear, but for ferromagnet it is not linear. Okay, for paramagnetic material. So what do you mean by this? Relation is not linear. See, if a ferromagnetic material is undergoing magnetization and demagnetization, then the curve of this induction curve does not follow the same path. I'll just tell you from here. So what I said, when a magnetic material, ferromagnetic material, suppose ferromagnetic material is being kept at certain region and externally applied field is increased. Okay, it is increased. First it is increased and go up to saturation. Saturation means when the magnetic induction or magnetization inside the material is maximum. You just go till then, and then thereafter you just reverse the field to make the field zero. That means when a magnetic material is magnetized by applying external field and the material is demagnetized by removing the applied field, then the induction curve does not follow the same path. Okay, look here. So this is called initial buildup or virgin curve. It is called virgin curve. You learn this in your higher standard when you do this experiment, BH loop, in graduation. So suppose the magnetic material was initially demagnetized. That means there was no magnetic field. See, no magnetic induction initially. Okay, initially at this point O. Okay, now external field is, see, this is the external field. So this curve is actually called BH loop. Okay, hysteresis loop or BH loop. What it is called? BH loop. I will say why it is called loop. So at least you can see that B is plotted in the y-axis and H is plotted in the independent
ರಾಮ್ ಸೌಂಡ್ ಇಲ್ಲಿಯಪ್ಪ. ರಾಮ್ ನೋ ಸೌಂಡ್.
Hello.
Yes, now I can hear Ram.
What about now?
Now it's okay.
Is it audible now? Is it audible? Okay, fine. So we could see the soft magnetic materials are those where the magnetic induction vanishes as soon as the magnetizing field is withdrawn. And soft magnetic materials can exhibit large saturation magnetization. Soft magnetic materials can be easily magnetized or demagnetized. And few more points we can write. So low remnant magnetization, okay, or we can say less remnant magnetization, remnant magnetization or induction. And the important point is that low coercivity. Okay, so soft iron, like examples of ferromagnetic materials are soft iron, and then some alloys like iron silicon alloys, nickel iron alloys, and soft ferromagnetic materials. So these are soft ferromagnetic materials. Okay, soft iron, iron silicon alloys, iron nickel alloys, etc. And where are these soft ferromagnetic materials being used? They are being used in solenoid, like where electromagnet is being used, like is being designed. So core, as a core, soft magnetic materials are used. Okay, cores of solenoid in electromagnet. Okay, and also they are used for making generators. Okay, generators. Sorry, not generator, transformer. I'm sorry, transformer. Core of the transformer. Transformer core. Transformer core. And hard ferromagnetic materials are those which retain their magnetization even after withdrawing the magnetizing field. So they retain a good amount of retentivity, and coercivity also is high, and have a high loop area. That means so large loop area or high hysteresis loss. So examples are steel bar, lodestone, alnico. Alnico means aluminum, nickel, and cobalt alloy. So alnico, aluminum, nickel, and cobalt. They are alloys of this alloy of this aluminum, nickel, and cobalt is hard ferromagnet material. Okay, and these hard ferromagnetic materials are actually used to design permanent magnet. Okay, now I'll just briefly discuss. Okay, this I have already discussed. I'll discuss the qualities or the characteristics of ferromagnetic materials used for making permanent magnet. So high retentivity, it should have high retentivity. That means even after the magnetizing field is withdrawn, the magnetic materials should have a strong magnetic field or remnant magnetization, that is called retentivity, so that it does not become zero. It retains its magnetization. High coercivity. High coercivity is required because it should persist its magnetization for long time even after the removal of external applied field or magnetizing field. Not only that, coercivity should be high, otherwise due to temperature fluctuation or some stray field at the region, stray field near the permanent magnet may make this magnetization zero. Okay, so stray field or temperature should not reduce its magnetization to zero. So that's why coercivity should be large or high coercivity. And high permeability is required in this case also. So in case of soft ferromagnetic materials, permeability is really high, but in this case also permeability, that is mu, that has to be very large. Okay, that means permeability high means, you know, it will be easily magnetized. Like if you apply a small field, the magnetization will be very large value. Okay, magnetization will be of large value. Okay, so these are three things, like these are necessary characteristics of a magnetic material to design a permanent magnet. That means, you know, you have to use a hard ferromagnetic material for making permanent magnet. And in case of transformer core or electromagnetic, like in solenoid core is used as like core soft ferromagnet or ferromagnetic material or soft iron. One among them is soft iron is used in solenoid as core. All right. So now we'll see, there was a question in JEE Mains paper 2016. JEE Main 2016. JEE Main. (2016). You can see this figure. So this is A, material A. So this is material A and this is material B. So the options were, first option, see, we have to choose the proper or the correct option here. Okay, first option says A is used for electromagnet. A is used for electromagnet and B is used for making generator. Okay, for making generator. A is used for transformer and B is used for generator. So A is used in transformer and B is used in generator. Option C is saying B is used for electromagnet, and A is used for sorry, here A is not there. B is used for electromagnet and transformer, and for transformer. And D, option D says A is used for electric generator and transformer. Used for transformer, and generator. I have already discussed about the use of soft and hard ferromagnet. You can see this is actually, so B is actually a soft ferromagnet. Soft ferromagnet is used in electromagnet and transformer, and hard ferromagnet is used for making permanent magnet. Sorry, hard ferromagnet. So hard ferromagnet is used for making permanent magnet and generator. But here A is electromagnet, this is wrong. A is used for transformer, this is also wrong. And B is used for electromagnet and transformer, this is correct. And A is used for transformer, this is also wrong. So that's why the option C will be correct answer. Now we'll take up one numerical problem from here. In JEE paper, JEE mains 2017. See what is given: a magnetic needle of magnetic moment, a magnetic needle of magnetic moment, I am writing directly M, magnetic moment 6.7 into 10 to the power minus 2 ampere meter square, and moment of inertia, I am writing directly I. Moment of inertia of the needle is I is given as 7.5 into 10 to the power minus 6 kg meter square, is performing simple harmonic motion SHM in magnetic field in B, like in a region where there is magnetic field of 0.01 Tesla. Time taken for 10 complete oscillation is, for 10 complete oscillations is, options are 6.65 second, B is 8.89 second, option C is 6.98 second, option D is 8.76 second. So you have to find out For 10 complete oscillation, how much time this magnetic needle will take, compass needle or magnetic needle will take? So you know this is uh, oscillation of compass needle near a magnetic field or in a region of magnetic field. So that we had already studied, right? So time period will be 2 pi root over I by m b h. H is the horizontal magnetic field of the earth. Okay, so here magnetic field is given. See what are given: I is given, m is given, bh is given. So we have to first find out for one complete oscillation what is the time period. Okay, this is answer. So this is the formula. If we put all these values, 2 pi root over I is 7.5 into 10 to the power minus 6. Okay, then m is 6.7 into 10 to the power minus 2, and this is 1 into 10 to the power minus 2, right? So we have to do the little bit of calculation here. After doing this calculation, see, you will get this value something like, so 2 pi, let it be here. This will give you around 1.06. Okay, this square root part, this is in seconds. So 10t will be 2 pi. So this is, there will be 10 here, 2 pi by 10 here. Okay, so 2 pi by 10 into 1.06 into 10. So this 10 will cancel each other, and so this 2 into root pi into 1.06 will give you 6.65. Okay, this will be 6.65 second. Okay, so this is how we have to solve numerical problems related to this thing. Okay, so we can take up one more numerical problem. The dipole moment of a circular loop, the dipole moment of a circular loop carrying current I is m, and the magnetic field at the center magnetic field produced by the circular loop at the center is B1. Now when the dipole moment is doubled without increasing the current, the magnetic field at the center is B2. Then what is the So B1 by B2 is how much? You have to find out. Options are given here. 2. Option B is given as √3. Option C is √2. And option D is 1 by √2. So this is actually from JEE Main. (2018). Okay. So I'll explain you what the question says. See, it says that the dipole moment of a circular loop. So what is the dipole moment of a circular loop? Suppose this is M1. M1 is I into A. Okay, I into A. A means what? I into pi r square. So this is equation number 1. Second thing, when the magnetic moment is doubled but without doubling. See, this is M2 is actually now 2M1. How we can get this 2M1? Yeah, we can get this as the I into pi √2 into r whole square. This would give you 2M1, right? Just look here. So we can imply that now the R2 radius of the loop, circular loop, is becoming √2 into r. So this is the clue. Now see, we know a loop produces magnetic field at the center B is given by mu0 I by 2r, I guess 2r. Okay, so mu0 I by 2r. So this is B1, this is R1. Now this is B2 is mu0 I by 2r2. So now let us take the ratio B1 by B2. Okay, mu0 I by 2r1. R2 is here. Mu0 I is not changing. So 2 goes up. So R2 by R1. So R2 by R1. So R2 is actually √2 R1. √2 by R1. So it is √2. So this is the answer. Okay. The ratio is √2. B1 by B2 is √2. So this is how we have to solve problems related to this particular chapter. Okay. So there could be various other types of problems also from the Curie law, etc. There will be problems from so from the Curie law, from this particular thing, and also from bar magnet. Okay, so that's we complete this chapter, magnetism and matter. In the next class we will start magnetic induction. Okay, so thank you for your patience. Bye for today.